So today we start chapter 6. And chapter 6 will end up being our most important chapter that we cover because it deals with the normal distribution, which is the most important probability distribution. And it's a continuous distribution, and pretty much for the rest of the class we'll refer back to this chapter and we'll use information from this chapter. So make sure you stay right on top of everything in chapter 6. It's going to be, it's not really overly difficult or anything, but it's definitely a very important chapter. So to start off here with our handout, we talk first about discrete random variables, which we talked about in chapter 5. And if you remember, we said that discrete random variables can take on only a finite number of values or a countable number of values. So the one that we talked about a lot was maybe a coin flip with the binomial distribution. So our random variable would be x, right? Or when we used our calculator, r. And for a coin flip, the random variable can take on only two values, right? Heads or tails. But a discrete random variable in general can take on plenty of values, but a finite number, right? And most of the time it's going to be an integer or something nice to work with. So some examples of discrete probability distributions. Well, the one that we studied was the binomial distribution. This was in section 5.2 and 5.3. Some other ones that I'm going to mention, some that you may see if you take another class, another stats class. You would probably see this one, which is called the Poisson. It's actually covered in our book in 5.4, and it's used to model wait times in lines for call centers or at the bank, grocery stores. So it's a fairly popular one. The binomial distribution is probably the most popular discrete distribution, which is why we study it. Another one that you may run into is the geometric distribution. That one's talked about a little bit in our book also. Hypergeometric. And one that's called the negative binomial. So there's a lot of them out there, and some of you will see others, but the one that we studied, the only one we studied, was the binomial distribution. But now we're switching. So before we were working with these discrete random variables, now we're going to move on to continuous random variables. And for us, this will be more important just because there's a lot more applications for these. So from chapter 6 and on, we pretty much only study continuous random variables. So if you remember, with a continuous random variable, these can take on any of the countless number of values on a number line. So some of the examples we looked at to talk about continuous as opposed to discrete. Discrete may be like a random variable x could represent the number of students in a classroom, where you're going to have an integer, where a continuous random variable could be the weight of a table, and realizing that we don't need to necessarily round it to the nearest kilogram or anything like that, or pound. So really it could be on a scale, right? It could be maybe it weighs 172.439 pounds, right? So continuous random variables can take on any of the countless number of values on a number line. The first one that we look at is the normal distribution. And this is going to be the most important one. So this one, we'll just say this for now. For now, we'll just say the normal distribution, or the Gaussian distribution, named after a German mathematician who studied it, is a probability distribution of a continuous random variable okay, but it's not just any one, it is the most important one. It is used everywhere. You'll see the normal distribution all over the place. It can be used anything from estimating the lifetime of a light bulb to the height of human beings. It's just all over the place. And you probably have heard about this bell-shaped curve. So the graph of a normal distribution is called the normal curve. It's sometimes referred to as the bell-shaped curve for obvious reasons. And there's some important properties that we need to be aware of with this. So one of them is, well, let's see, the curve is bell-shaped with the highest point over the mean. So if you look down here, we've got the mean here, and it's the highest point of the curve. And you can see there's a symmetry here. And then look what this is, the mean plus sigma. So this is mu, right? So this is the population mean, and then this is sigma, the population standard deviation. So we've got this bell-shaped curve broken down into parts. So we've got the mean here, got the mean plus 1 standard deviation, got the mean plus 2 standard deviations, then finally the mean plus 3 standard deviations, and it goes back this way too, the mean minus 1 standard deviation and so forth. So the curve is symmetrical about a vertical line through the mean, mu, so there's a symmetry here. And let's see, the parameter sigma, which is the standard deviation of the population as we know, controls the spread of the curve. So one thing that we'll see a lot is if the standard deviation is large, the curve is more spread out. So if you have a large standard deviation, then you'd have a curve that would be maybe more like this. It'd be more of a spread out curve, something like this. Okay, so we'll see that as we get into this more. The curve is asymptotic to the horizontal axis. Who remembers the good old days in algebra finding horizontal asymptotes? So if you remember what that means, it would mean that the line is approaching the asymptote, but it never touches it. Now, of course, there's cases where it will cross it and things like that, but let's just look for the simplest idea right here, where this curve, this bell-shaped curve, technically it never touches this horizontal axis. It gets infinitely close, and it gets there pretty quickly. I mean, you can see at 3 standard deviations above the mean, it's almost touching it. By the time you get to 5 standard deviations above the mean, it's so close that our calculator can't tell that it's not touching it. But technically, it never touches it. And then this is the part that's really important for us. The area under the curve is 1. The reason this is important is because we are going to use this curve to figure out probability questions. So we're going to use this as every number on here could be a possible outcome to an experiment or a possible value for a random value. And we know that if we sum up all the probabilities of all the outcomes, we have to get exactly 1. And so the area under this curve is exactly 1. So there's going to be a correspondence between the area under this curve and answers to probability questions. So it had to be that the area is exactly 1. And if you look at this curve and look what it looks like and realize that it never touches, making this exactly 1 is not a real easy task. And some of you, if you're super lucky, you'll take calculus 3, and when you have multivariable calculus, you'll be able to show that the area under this curve is exactly 1. But for us, we are just going to avoid that, so we don't need to prove it. We just need to be aware of it. And then here's the empirical rule. And I'll mention it here, then I'll refer to it on the curve above. So here's numbers that we need to, for this section, get really familiar with these 3 numbers. The empirical rule. So basically in practice, right? The empirical rule through experiment or noticing things in practice or through experimentation, this is what tends to happen. For normal distributions, so for things that follow a normal distribution, approximately 68% of the data will lie within 1 standard deviation on either side of the mean. So 1 standard deviation above to 1 standard deviation of below. So in the curve up here, what that means is basically from here to here, right? This is 1 standard deviation below the mean, 1 standard deviation above the mean. And right in here, about 68% of the data are going to be right here, within 1 standard deviation of the mean. Okay, so then if you keep looking here, then it shows that about 95% of the data will be within 2 standard deviations of the mean. So if I go out another standard deviation above and below, so we get to here, right, then this area here, if we get all of this area here, that's going to be about 95%. So there's about, maybe do it like this, about 95% of the data here. So 68% within 1 standard deviation. By the time you get to 2 standard deviations, you got about 95% of the data. So we'll see that human height follows a normal distribution, which means that 95% of us have a height that is within 1 standard deviation of the mean. And then finally, if you get out to 3 standard deviations, so by the time you are out to here, to this area here, you're going to get almost all the data. By the time you get up to 3 standard deviations from the mean, you will get about 99.7% of the data. And that is for anything that follows a normal distribution. And we'll see that many things do. So for now, let's just kind of get familiar with these numbers. You're going to see them a lot in section 6.1. And 6.1 is a fairly basic introduction. So they start off slow in chapter 6. 6.1 is a very basic introduction to the normal curve. And they're going to get us familiar with these numbers. And then later we'll see how to move off of this. Like, we don't want to always just know exactly 1 standard deviation above or 1 below. So we'll learn how to move off of these as we get into 6.2 and 6.3. So on the next page of the handout, get ready to see what I'm sure you will agree is the best looking formula you've ever seen. Okay, are you ready? Look at that. You got to admit, when you look at that, I know you're thinking, dang, he's right. That is a good looking formula. Now, before you rush out and get a neck tattoo, just let me warn you, make sure you have secure employment first, okay? I get that a lot. Students are like, man, I really like it. I'm going to get a neck tattoo. But you want to think about that. Get good employment first. So this is the formula for the normal curve. And it's a little rough, right? But remember when I mentioned that it's really difficult to make that area under the curve be exactly 1? Well, this is how you do it. It turns out that if you integrate this curve, if you have taken calculus, you know what that means. If you integrate this curve from negative infinity to positive infinity, you'll get exactly 1. And that is not an easy integration, but it's not too bad if you've taken Calc 3. But for us, if we wanted to graph the normal curve, we could graph this in the graphing calculator, but it's really difficult. It's really difficult to put these in here with the order of operations working correctly. That's actually a negative right there. But there's an easier way. So I'll show you how to do it on the calculator just so we can see it. We're never really going to have to graph this. But I'll show you just so you can see what it looks like on your graphing calculator. Okay, so if we want to see the normal curve on the calculator, what we can do is go to the y equals screen. And notice that the plot is turned on this one, so I want to turn that off. So you go up to the plot and hit enter. And come back down. So we're going to want those turned off. We're going to want everything cleared out of here. If there's anything in there, we want to clear it out. And then from here, we're going to go where the distributions are. Remember when we went to binomial PDF or binomial CDF, it was the second vars. We go in the same spot, so you go second vars, and the first one right there, normal PDF. This is the only time we'll ever use normal PDF. You'll see why later, but we're always going to use normal CDF for doing any kind of questions in this class, but just for the graph, only for the graph we use normal PDF. So I just select that. And then depending on the software, there's two versions. So if you don't have this version, just hold on a second and I'll do your version. If you have this version, for the X value we need to put X. So we press this X right there, that button right there, press that. And then we can keep mu as 0, sigma is 1, and then hit paste. So that's in there. But to set it up right, we're going to need to set the correct window. So if you go to the window key, and let's go for X, let's go -5 to 5. So you need a negative. That's this, right? Don't hit the subtract. Hit the -5. And then enter to 5. Put a tick mark every 1 unit. That's fine. That's the scale. For Y, let's go 0 to 1. So let's go minimum of 0, maximum of 1. And this stuff doesn't matter. I'm just going to put a 1 here so it doesn't put tick marks on it. Then from there we can hit graph. And it shows a bell-shaped curve. So if you had the other version, it'll just be pretty similar. Go to Y equals, let me just start from scratch. I'm going to get rid of the plot. So I go to same thing, second vars, I hit normal PDF. With this version, this comes up. So you just hit X, comma, 0, comma, 1, close parenthesis. You can hit enter if you want to. Then we go to the window and do the same thing. We'll go from -5 to 5. And for Y, we'll go from 0 to 1. And that scale doesn't matter. If it puts a tick mark every 5 units, it doesn't matter. It won't show anyway. So just hit graph. So that's just if you wanted to see the normal distribution on the curve. We're not really going to do anything with the graph of that, but that's how you would graph it on these calculators. So one thing you may have noticed when we were working with the graph is the normal PDF, we had X, 0, and 1. We had 0 for mu and 1 for the standard deviation sigma. So I'm going to do one more video because I want to show you what happens as sigma gets bigger. Remember, this is the spread of the data. So if the data are spread out more, if I make this bigger than 1, I should get a curve that's more spread out. So let's just try it on the calculator and see what happens. So we have the calculator here, and this is the one we graphed with normal PDX, X, 0, and 1. So remember this 1, that's a standard deviation of 1. So I'm going to do another graph with a standard deviation of 2 just to see what it looks like. So I'm going to do the same thing. I'm going to grab the normal PDF from the distribution menu. So you go second, distribution, select normal PDF, and I can go down and just change sigma to 2, and then hit paste. And I'm just going to graph both of them. So I'm just going to hit graph. And there's the first one and the second one. So this is the one with a standard deviation of 1, and now this one has 2. And it's just, see how it's spread out more. It's just a spread out standard. It's still a normal distribution, but it's way spread out. So the thing to keep in mind, the area under the original curve is exactly 1. The area under this curve is also exactly 1. So the probabilities are still all there, they're just spread out. You can see this, the normal distribution curve with 1 standard deviation cuts down quicker. With 2 standard deviations, the data are more spread out. But the area under the curve, and each case is still 1. So what we'll do now is we'll take an example, our first example of the normal curve. And we're going to start with heights, the heights in inches of men and women in the United States. So let's fill this in. What is the mean height of a United States woman? Take a guess. What do you think? If you're thinking around 5'4", pretty good. 63.7 inches. And the standard deviation there is about 2.8 inches. What about for men? What is the mean height of an American man? If you're thinking around 5'9", pretty good. 69.3 inches, and again, standard deviation is 2.8. Now these numbers will vary a little based on the source, but most of them will be pretty close to this. So here's some interesting data. So the tallest, let's see, I've got information about where the tallest people in the world are from. So let's see, Denmark and Netherlands. Denmark and the Netherlands also are a couple areas where people are very tall. So the average male, guess how tall? 6 feet. That's the mean height, 6 feet. Guess how tall the average female is? 6'7". No, kidding. That would be really tall. But still, 5'7". 5'7". So that's really tall, right? For the mean, 5'7" for a woman and 6 feet for a man. And there's one area in the world that's a tiny bit taller, and this is in the Dinaric Alps. And it's a region, I think there's a few countries there, but it's a little north of Denmark. And that's the tallest region for people on the planet. The average woman there is 5'7.5". That's average, 5'7.5", and the average man is 6'1". So pretty tall. Worldwide average. You guys ready to take a guess? The worldwide average woman is 5'3". Worldwide average man, 5'8". So here are the heights that we're going to use, though. For an American woman is about 5'4", American man about 5'9". Because remember, there's 60 inches in 5 feet, right? Because 12 inches in a foot. So what we want to do is use this these numbers right here to figure out how this breaks down then with what we know about the standard normal curve, because heights of people follow the normal distribution really closely. So then using this graph and using these numbers up here, we want to figure out how people fall into these categories. So this is a table, or this is a picture of the graph that's pretty close to the one in the book. The one in the book that's a little nicer just because it's color coded is page 275, and it has something like this where it's color coded. Now you notice that here, this is just where this particular graph decided to round. So the number we use is 68. We use 95 here and then 99.7. So this just has another significant figure. So it doesn't matter. Our book will use 68, 95, and 99.7 as our three, kind of like magic numbers for this. So this one is just a little different. They just rounded to the first decimal place for all of these. So how this works is, I'm going to start here with the mean. I'll start with the mean height of an American woman is 63.7. So I'm going to write this right here, 63.7. And then I'll make a little line here. And then the men's height on average is 69.3. I'll put this right here. And then what we want to do is just, where I can see this whole thing, is move along this distance here. So for an American woman who's 1 standard deviation above the mean, we just add 2.8. The standard deviation is 2.8 for both. So for 63.7 plus 2.8, I have 66.5. So that is like 5'6.5". So if you're 5'6.5" as an American woman, that means you're 1 standard deviation above the mean. So if you keep going here, add 2.8 in each direction for the women and for the men, and then subtract 2.8 going this way, you should be able to fill these in. So go ahead and take a minute here and fill those in, and you should get something like this. So these are the heights in inches, and again the mean is right here, and then we can see out here, so this is just over 6 feet tall. So if an American woman is 72.1 inches, which is just over 6 feet, they would be 3 standard deviations above the mean. And for an American man, so 77.7, so again 72 inches is 6 feet. So it'd be just under 6'6", right? It would be 3 standard deviations above the mean. So if you put this all together and we look down here, these numbers down here, this is roughly 4'7". This is about 5'1". This is about 6 feet, about 6'6". So this is 3 standard deviations above the mean. And here's the number here. We know that for populations that follow the normal distribution, and heights of human beings is one of those populations that does, that means 99.7% of human beings will be within 3 standard deviations of the mean. And 95 or 95.4, if you want the extra decimal point, are within 2 standard deviations of the mean. And finally 68% or 68.3 are within 1 standard deviation of the mean. So what that means is, just looking at this, 99.7% of Americans for women are here between 4'7" and 6 feet, and for men 5'1" to 6'6". So what that means is, with 99.7, that means that if you had 1,000 randomly people selected, if you just randomly picked 1,000 American names, only 3 of those people wouldn't fit in here on average. You know, there's a variation built in and randomness, but just generally speaking, out of 1,000 random people, only 3 of them wouldn't fit in here. So it's just an example, our first example of a normal distribution using human heights. You may even be thinking, I wonder what the perfect human height is. Well, after careful study, it's been determined that the perfect height for the perfect human being specimen is 5'8". Can you believe it? No, I made that up. Guess how tall I am. I'll give you a hint. It might be 5'8". Sorry about this bad humor. I'm just trying to keep you guys awake. This is what happened to my star pupil. He couldn't take it anymore. He fell asleep. Usually it only takes me talking for about 2 minutes before many of my students get just that sleepy. So let's, before you guys get that sleepy, let's try a few of these in the homework. And it's, like I said, 6.1 starts off pretty basic, so I think you'll probably be okay, but we should look at a couple of these. Also, I'll mention another thing, there's actually these wear patterns that you can see sometimes that have the shape of this bell-shaped curve. So if you guys ever go to like an old building, you know, and it'll have these old doors, and sometimes they'll have this like a copper plate. So there'll be this copper plate. So I think you probably know what I'm talking about, these old doors. Well, You can see a bell-shaped curve wear pattern in here because people typically press in the same spot. So there'll be a wear pattern that a lot of times will look like this kind of bell-shaped curve. And you'll see like it'll be wore in here in a bell-shaped curve fashion. I would bet some of you even purposely don't push there because you know other people do. And you don't want to get germs. I know some of you are thinking, I definitely don't push there, right? But the wear patterns you can see in things like this, things that are old that get a lot of wear, you'll see a bell-shaped curve appear in many of these. One thing you'll see in the book too that we don't cover is 6.1. They cover control charts. These are used extensively in manufacturing for quality control. I remember even having to use those a long time ago. But the book covers them. We just don't cover them in this class. But what we should do is take a look at number 6. So let's take a look at number 6. And for number 6, there's, again, there's a pretty nice picture on page 275 of the book. And on there, it's figure 6.3. In figure 6.3, it's basically a bell-shaped curve broken down where it shows the 68%, 95%, and 99.7%. It's just a better picture of the one that's on this handout. And it's color-coded, so it makes it a little easier to see. But using that, for number 6, they want us to answer a few questions. So question A says, what percentage of the area under the normal curve lies to the right of mu? To the right of mu. Well, to the right of mu, if you think about what this standard normal curve looks like, something like this, and mu is right in the middle, right? So the percentage of the area under the normal curve to the right of mu, what's that going to be? It's exactly 50%, right? 50% of it is here and 50% of it is here. So for part A, it's 50%. 50% lies to the right. Then part B says between mu minus 2 sigma and mu plus 2 sigma. Okay, so that's another pretty basic one. So we've got our normal curve. And we got mu, and then we basically have 1, 2, 3, right? This would be mu plus 1 standard deviation, mu plus 2 standard deviations, mu plus 3. And then the same thing over here, right? Mu minus 1, minus 2, and minus 3. And so if they say between mu minus 2 sigma, I guess I better write it like this. 2 sigma, 3 sigma. So they're saying basically between here and here. And that one we know is 95% roughly, right? 95% is in there. So for part B, it would be 95%. So we got 50%, 95%. Then part C, this one's a little tricky. So part C is a little trickier. So if we draw the picture for part C, it says, let me draw this first. So we've got 1, 2, 3. And of course, this is mu plus 1 sigma, mu plus 2 sigma, mu plus 3 sigma. It's kind of hard to draw those. And then this thing to the right of mu plus 3 sigma. So to the right of here, which is just this little like tiny spot right there. So what is that? What percentage of the area under the normal curve lies there? So see if you can figure it out and then check back. So hopefully what you did is something like this. I'll use this different color here. You're saying, well, I know that between here, all of this is 99.7%, which leaves only 0.3%, right? And half of it's going to go here and the other half is going to go there. So if you divide this by 2, you get 0.15%. So that means there's 0.15% there and also 0.15% here. So the answer to that one is going to be 0.15%. Okay, so hopefully you're okay with that. That one was probably the only one that's a little bit tricky, because they just want the percentage area to the right of this point, and to the right of there's not much left, right? Not a whole lot left there. Okay, for this next one, we need to look at page 274, which is, it's under this guided exercise 1, but I'm just going to ask you a couple quick questions about the graph. It says figure 6.2, and it basically, I can just draw, basically looks like this. They've got this graph A, which is tall and pointy. And they have this graph B. Now they both are centered at the same spot. But graph B, I'll make that red, is really spread out, short and kind of spread out. This is graph B. Actually, my drawing's not that great, but if you look on page 274 of the book, or figure 6.2, you'll see it. So here's the question. What is the mean of figure A, of graph A? You can see it's 6, right? The mean of graph B, also 6. So the means are the same. So which one has a larger standard deviation? We have to know B, right? B has a larger standard deviation. It's more spread out, right? Graph B is more like team 2 when we talk about team 1 and team 2. Remember team 1, that basketball team, they're all about the same. They were all about the same height, where team 2 was all spread out all over the place. So curve B has a larger standard deviation. It's more spread out. The pointier the normal curve, the smaller the standard deviation. So this would be more like team 1. They're all roughly the same, whereas graph B is spread out all over the place. Now remember, if these were drawn correctly, which my hand drawings are not, but if they really were normal curves, the area under each curve is still exactly 1, right? The areas are still 1. They're just they're spread out differently. And there's probably one more we should take a look at. Problem number 8. Let's take a look at problem number 8. And problem number 8 talks about Rhode Island red chicks. The incubation time for Rhode Island red chicks is normally distributed. So the incubation time is normally distributed with a mean of 21 days and a standard deviation of approximately 1 day. So we could actually draw this out. If we know they're normally distributed, then we know there's a bell-shaped curve here, right? There's a bell-shaped curve. And we know that the mean is 21 days. And when they tell us that they're normally distributed, that means that if we go out 3 standard deviations above the mean, we're going to get about 99.7% of the data, right, between that and 3 standard deviations below the mean. So it tells us the mean is 21 days, so here's our mean. Our mean is right here. And it tells us that the standard deviation is 1 day. So if I go 1 standard deviation above the mean, I'm at 22 days. 2 standard deviations would be 23 days. 3 standard deviations is 24 days. And if we go below, we have 20, 19, and 18. So this one's pretty nicely distributed, where the standard deviation is exactly 1 day. So just looking at this and knowing what we know about the standard normal, or about the normal distribution, we know that about 99.7% of those chicks will hatch between 18 and 24 days, right? Because it tells us that the incubation time is normally distributed. The mean is 21 and the standard deviation is roughly 1. So based on that and the fact that it says 1,000 eggs are being incubated, and assuming, of course, they'll all hatch, how many chicks do we expect will hatch in? And then part A says 19 to 23 days. 19 to 23 days. Well, 19 is here, 2 standard deviations below. 23 is 2 standard deviations above. So 2 standard deviations below to 2 standard deviations above, that's 95%, right? So 95% of 1,000 would be about 950 chicks, right? Now, if you use the other chart, you know, they had 95.3, or actually 95.4, so you'd say 954 if you use the other chart. That's not really important again. But our book will say the numbers that our book uses are 68%, 95%, and 99.7%. So when you look in the back, for 6.1, it's not going to matter when we get out of 6.1 because you won't be stuck right on 1 standard deviation. But for 6.1, they're going to be using these numbers. So using those numbers, we get 950 chicks. Then for part B, it says, how many chicks do you expect will hatch in 20 to 22 days? Well, 20 to 22 days, that's only 1 standard deviation below and 1 standard deviation above, right? So that's going to be, we'd expect 68% of those chicks, or 680, right? Because there's 1,000 chicks, so 68% of that. Part C says in 21 days or fewer. Well, here's 21 days. It's right down the middle. 21 days or fewer, half of them, right? 21 days or more, half of them. So when they say 21 days or fewer, that's all of these chicks. So there's randomness built in. So, you know, some chicks are going to hatch in only 18 days, where others will take 23 days. So this is the mean. So 21 days or fewer, half of them, which would be 500 of those, right? 500 of the eggs will hatch. Then part D says, in 18 to 24 days, assume all eggs eventually hatch. So 18 to 24, so that is from here to here. So that is 3 standard deviations below the mean to 3 standard deviations above the mean. So now we're here. 99.7% of those, or in other words, about 997 of those will hatch. So that should get you started. Remember, Chapter 6 really is the most important chapter for us. And it starts off 6.1 isn't too bad, so just make sure you stay right on top of Chapter 6, because we'll need to know this for the rest of the semester. So give it a shot, and of course, if you have any questions, just let me know.